k boxes. So that gives you the q raised by. So if you add these two chaps up, if you add this and this, you should get this. That's the idea. So I still want to continue because in your questions I got confused. So we want to clarify something. I mean, this proof, whatever I just wrote, was exactly the same as binomial theorem, right? I mean, we delete the last guy and then we get two buckets. That was the whole idea. So we just proved this theorem that n plus 1 choose k, q is q raised per k, and choose k, q plus n choose k minus 1. And then I said that this is equal to this. And today I was a little bit confused that I had said that, so this was 1 and this is 2. And I had said that, so we said 2 follows from 1 by symmetry. And the symmetry was n choose k is equal to n choose k minus 1. But let's call this 3.
N minus k, Professor.
Yeah. Sorry, n minus k. Is that what you're saying?
Yeah, that only, Professor.
Okay, but this, so I got confused. But this symmetry is deeper. I mean, it's not so obvious. When I thought about it this morning, I thought this is not so obvious. As I thought yesterday. Anyway, I think I figured it out, but I will indicate it later. I mean, I've half figured it out. And maybe I can leave it as a homework. So that would be the best thing to do for me, I think. But we'll see. So now what I'll do is I will show, let me show 2 and 3 by another technique. Okay, so again, let's say another and rather more complete proof of 2. Okay, so this is what we had. This is also very easy. I mean, everything is, this game is quite easy, but this is what we had. We're expanding x plus y raised per n plus 1 and we get the left hand side. So just multiply by this, and this is equal to x plus y times sum k going from 0 to n, and choose k q x to the n minus k y raised per n. Fine. And on the other hand, this chap, well, let me expand it out. So this is k going from 0 to n, and choose k. I mean, this is less combinatorics and more n minus k plus 1 y raised per k plus summation k going from 0 to n, and choose k x to the n minus k plus 1. So there is a y here, sorry, to include that. So y x to the n minus k plus 1 and then y is okay. And this is the first term is the same. And choose kq x to the n minus k plus 1 y is for k. And the second term is so y is shifting x n minus k plus 1 times it crosses x minus n minus k plus 1 times, so it generates a power of q.
So, Professor, I think shouldn't that be n minus k
Sorry?
in the second term, the power of x?
Yeah, you're right. You're right. N minus k, right? No, wait. This was um, yeah, yeah. So this should be this fine. This one is wrong, and this is n minus k, and then y raised for k plus 1. Yeah,
Yeah.
that's fine. And this side right here is summation k going from 0 to n plus 1. And I have a weird color, which you can't see. Oops. So this side was summation k going from 0 to n plus 1. N plus 1 choose kq x to the n plus 1 minus k y raised for k. So now all we do is compare coefficients of x to the n plus 1 minus k on both sides to get, on this side you'll get n plus 1 choose kq. This one you'll get n choose k q. And here you want, this is k plus 1, so you want raised for k, so you want k replaced by k minus 1. So you get q raised for n minus k plus 1 and choose k minus 1. And that does it. So that's an alternate proof. And well, just okay. Well, so the remark is if you do x plus y raised for n plus 1 equal to x plus y raised for n x plus y, you get the other one. So in any case, this um, um, so this proof is more analytic, but there is a combinatorial explanation which I really like. So that's why I did the first one, and then we still have to figure out the second one using combinatorial. And one thing I should note is that when you do this kind of thing in the binomial theorem, you don't get two things. You just get one thing. You just get the Pascal's triangle. So there will be an exercise later, I think. And you can play this game with other polynomials. So um, we'll get to that. So then you recall that there was an exercise which I gave at the last time, which was n choose kq is 1 minus q up till 1 minus q raised for n, and 1 minus q up till 1 minus q raised for k. This whole thing multiplied by 1 minus q up till 1 minus q raised for n minus k. It's not visible. Maybe I can do a smaller one. So there's some notation which we use. This is kind of inconvenient. It's called Q rising factorials. I have my handwriting on that. So AQK is defined to be 1 if k is 0, and it is 1 minus A, 1 minus AQ, and so on till 1 minus AQ k minus 1. Here. If k is bigger than 0. So empty product I take to be equal to 1. And this is Q rising factorial. So what we have here, so n choose k q is q sub k, replace a by q, q sub n, sorry. Q sub k and q sub n minus k. Yeah. Thus, we know this. From this formula, this is obvious. So this is fine from this formula, the formula that you calculated. And note that the limit as q goes to 1 of q raised per a. So replace a by q. This is a semicolon. I should make that clear. I write it so often that I've forgotten that it's not clear. So if you take the limit of this guy, and I divide it by q raised per k, so then I will get, so this see, if I replace a by q raised per a, this is a, replace it by q raised per a and divide it by 1 minus q. So this is the limit as q goes to 1 of 1 minus q raised per a, 1 minus q, 1 minus q raised per a plus 1 over 1 minus q, and so on. A plus k minus 1. Oops. 1 minus q, and this will come out to be a into a plus 1 up to a plus k minus 1. So this thing, so there is a notation for this too.
Professor, what's the last term?
This guy,
Yeah.
this is a plus k minus 1.
Okay, all right.
So
Professor,
this chap should be a plus k minus 1 in the power. And so this is this notation, a plus 1 up till a plus k minus 1 for k bigger than 0, 1 if k equal to 0. This is called the rising factorial. The wrong spelling of rising.
Professor?
Or the, hang on, fork hammer symbol. Yes.
Yeah, so Preetham was asking if you could use a thinner nip, like a thinner thickness.
Sorry?
Thickness of the writing, if it could
The
be a bit
pen.
less. Yeah.
You don't like my thick pens, do you? It's not going to improve my handwriting, that's for sure. But Anyway, let's try this one. Any other questions, queries? So, I mean, this is a generalization. 1 sub k is equal to 1 into 2 into 3 up till k. So it's k factorial. That is why it's called a factorial. So it's a generalization of the factorial, and it's clear that the limit as q goes to 1 of n choose k q, which is the limit as q goes to 1 of q q n divided by q q k q q n minus k. So you multiply and divide by appropriate powers of q raised 1 minus q raised per n. This limit will be 1 sub n, 1 sub k, 1 sub n minus k, or n factorial, k factorial, n minus k factorial. That you already knew. I mean, we already knew this. But formally, these things match, and that gives you your. But it's worth noting in any case. Okay, any questions so far?
Professor, could you go over the limit part on the top ones? I think I couldn't follow that.
Which part? This part? Here?
Yeah, that one. Yeah.
So yeah, I mean, what's there to go over? Let me use another color. Uh, Let me use pink. So you know that limit 1 minus q raised per a over 1 minus q is equal to a.
Yeah, it's fine, Professor. Yeah, now it's fine.
And this q raised per a and a plus 1 and so on comes from this definition. So I'm replacing a by q raised per a. So this is 1 minus q raised per a, this is 1 minus q raised per a plus 1 comes from here, and similarly plus k minus 1 comes from here. So a plus k minus 1, and then you use this.
Professor, when you've written Qn, is that the rising factorial symbol, or is that Q semicolon Qn?
Yeah, that's the q rising factorials. So
Okay.
those are q rising factorials.
But how did we get that?
How do we get what?
Uh, in the just after the equal to sign, what
Uh, I don't know which part you're talking about. This
right
guy?
there, right? The one above that.
Huh?
Yeah, that one. The denominator of that.
This guy?
Yeah.
Okay, yeah. Okay, I see what is bothering you. I didn't write the Q here. Okay, sorry. Yeah, I mean, if you look at my papers, they're all we use this notation without the Q for this guy whenever there's so there's all confusion. But thanks. Sorry about that.
Professor,
Yeah.
I had something to ask. So x and y, they don't commute in multiplication, but they commute in addition, right?
Yes.
So, Professor, if we write x plus y whole to the power n as y plus x whole to the power n,
Yes.
and if we expand both sides and compare the coefficients, then I think we would get the
Taking that.
this n choose k and n choose n minus k. These are equal.
Try it out. I think you get something else because you have y raised for n minus k and x raised per k then. Or I don't know. Actually, you'll get the same thing. You won't get anything. Try it out. Try it out
Okay.
and show me what happens.
Okay, Professor.
Yeah. I mean, I mean, you'll get something equivalent, but I don't know whether we get the second property or not. But you'll get something equivalent to whatever you got. So x plus y is certainly okay. So let's move ahead. So this is finishing up with last time's stuff, which we are still going to continue finishing up. So so one thing I want to note, want you to notice that if when we have q, so I think I mentioned this last time, when we have a q, we got an explicit formula, which we did not get, uh, in the case of Pascal's triangle. Um, in the case of the q equal to 1 case or whatever, Pascal's triangle. So this trick basically gave us two. Uh, this trick gave us two of these, right? This was the main idea. Where are we? Yeah, it gave us two of them at the same time, and that is what helped us calculate. So you can calculate now. You can set these equal to each other, and we left it as an exercise to calculate the value of n choose k, q choose with the q binomial quotient. So that wasn't available in the q equal to 1 case. So that is one note that you have. And then secondly, so there is an extra, there is an extra degree of freedom, which helps us. Okay, and the other thing is that the q, well, um, that I'll get back. Okay. Let me make some remarks. So remarks from the proof, whatever we got. So from the proof, we get um, that the number of east and north paths from 0, 0 to, now we take some general point, B is A plus B choose A or B. So A is basically the n minus k, and B is essentially the k. So so on the top you get n, so A plus B, and at the bottom you get the k. So this is what we get, and of course this is equal to A plus B choose A. So this is one. And further, these paths correspond to the binary string. So I mean, instead of writing 0, 1, 1, 0, 1, we wrote x, y, y, uh, x, y, and we may as well write east, north, north, east, north. So essentially, these are all the same thing. And the only thing is that there is no q commutativity here. So there is no, we are not counting the area. We are just saying all of them are the same. Earlier we were splitting them by area. So earlier we were saying that whatever the area is, we were keeping track of this area. Now I don't keep track of the area. I just take all the paths. When I take all the paths, I get all the binary strings. So in some sense, this queue refines the result. So let me just box this because this is meaningless otherwise. I should say that the non-commutative binomial theorem is thus a refinement of the binomial theorem. So what we have done is we have added a statistic called area under the path, and we are counting as per the statistic. By the way, this is due to Polya. This path to Q binary, this interpretation. So let me write it here. It's in Polya's book. It's due to Polya. So it's this kind of refinement is called Q analog, and it is this is quite common and I would say current theme in combinatorics. And let me say uh, special functions, representation theory, quantum group, physics, all kinds of things. So um, it is uh, called, so people who keep doing this stuff, they say that they have got the Q disease. And it has no cure. So beware. Anyway. Okay, so what I'm saying is that the Q business is quite current. It happens all the time. We keep doing it, and this is a all over. When you see papers on archive on combinatorics, you'll find a lot of Q analog of this, Q analog of that, and so on. And in all kinds of contexts, you add some kind of Q and you get some nice formula. It's not clear why this is such a pervasive thing. So when I did my PhD long back, it wasn't so pervasive. And people used to say that, what are you guys doing, and this and that and all that. Now everybody else is doing the same thing. So it's interesting that a lot of it's come up in a lot of current work. And anybody tries something and they get something here. So I should mention that the multinomial coefficient can be represented. So this is K. Oh wait, K1 plus K2 plus K3 on up till Kn factorial, K1 factorial, K2 factorial, and so on. And this can be, so this is written as this k1 plus kn, k1 comma k2. Okay, or n comma this, n choose all these with all these adding up to n. So this is also written like this. And this is the number of paths from 0, 0, n of them in n dimensions to k1, k2, kn, where the path has k1 steps in the x1 dimension, k2 steps in the x2 dimension, and so on. Kn steps in the n dimension. So imagine a path. I mean, you imagine the uh, in n dimensions, and you get. I mean, it's an obvious result. So nothing uh, nothing very serious to present here, to prove here. Okay, now I want to prove another theorem from here, and this is called a finite Q binomial theorem. So, I mean, it's a natural question that you have this non-commutative business. So, is there something commutative also about it? And one can derive from the other. Let me just write it down first. So, it's y q n is equal to k going from 0 to n minus 1 raised per k, q raised per k minus 1 choose 2, n choose k, q, y raised per k. So, there is no x in here. And there's just one variable, so there's no question of it being a um, you know there's no it's not non-commutative, it's commutative. So we start with we begin from here, x plus y raised per n is equal to k going from 0 to n choose k to x to the n minus k y raised per k. We replace y by x1. So what we note is that xy times x is this, I mean, it will work if this is equal to q times x times xy. And in fact, that's easy to verify. So, y has to, you can just do a associative law and then interchange y and x and get extra q. So this works. And then you see from, let's say, the left hand side, what happens. So x plus xy raised per n. What is that? This is x plus xy, x plus xy, and so on. X plus xy, x plus xy. So I don't know. I mean, there are n of these, right? And so here I can take out the x here, and it's 1 plus y. And then here it's x plus xy. In the next step, I can multiply the x here, so I get xyx, and then that can become x square y, and this will become x square. So I can take x square out, and I get 1 plus q times y, 1 plus y. And then the next guy will be, there is another one, x plus xy here. This will give me 1 plus y here, 1 plus qy here. And then I'm multiplying x square here, and y is crossing over two x's. So there is an x cube. So you get an x cube q square y. You will get a q square y here plus x cube, which I'm just going to take off. Keep going this way. And what you will get is x to the, how many are there? N. And you will get 1 plus y q raised to n minus 1 down to 1 plus 1. Is that clear?
Yes, Professor.
So yeah, it's very interesting, and I'll just write it the other way around. X to the n, 1 plus y, so on until 1 plus y q n minus 1. And so what do we get? We get x to the n, and then this one is minus y, or let me write the whole thing, because we're not used to the notation. 1 plus y, 1 plus qy, so on until 1 plus q raised to n minus 1y. And this is equal to, now here I'm k going from 0 to n, n choose k, and x to the n minus k, and xy to the k. Now, let me put it in different color. What is xy to the k? This is xy, xy, and so on, k times. So this y will stay on this side, but there are other, this y will, let's say, it travels all the way to the end, and there are n minus 1 x's it will cross. So this first y will cross n minus 1 x's, the second y will cross n minus 2 x's, last y will stay over as it is, and you'll get all these y's together, and you'll get all these x's together. Is that clear?
Yeah, Professor.
So this is 0 plus 1 up till n minus 1, so it's n choose 2. Is that okay? Everybody got that? So just think, there is a y here in the end. Let's say there's a xy term here. This y will go across 1x, so it will contribute to x raised q raised by 1. Let me put it here. So suppose these are k of them. This y will cross this x and get you y square here. This x will come here. The next y will cross 2x square, x square. So it will give you 2 q raised per 2, and so on. So this y will give you n minus 1. So you get this term. And now if you plug that in, I'm continuing the equal to sign. I'm going to get x to the k times x to the n minus k. So this x to the n comes out. It doesn't depend on n anymore. N choose k q, and then I just get a y raised per k. That's it. And I also get a q raised per n choose 2. No, k choose 2. Sorry, this is k. So Yeah. So I get x to the n here, this equal to this, and I just cancel the x to the n. And I get this, and then I replace y by minus y, and I get what I want. So I get y q n is equal to summation k equal to 0 to n minus 1 raised for k, q raised for k choose to n raised to y raised for. That finishes the proof. Okay, any queries on this? I mean, there's no combinatorics here, it's just manipulation. It's called manipulatorics. So, and then we adopted it. He said, you know, so I put it in a paper. Other people put it somewhere. Now it's very well-known term, manipulatorics. After doing some manipulatorics, you get this. So anyway, so here's an exercise which I'll probably add in the homework. Prove this by induction. So the binomial theorem proof in high school was by induction. So if you can prove this, so this is also a Q binomial theorem. And the point to be noted is that something to be noted here is that on the left hand side is a polynomial in degree n, polynomial in y of degree n. And this is an expansion, right? So same thing with the this guy, 1 plus x raised power n. So you have a polynomial of degree n and polynomial here. So since I just came from Bhatia's class, these guys, 1 x, x square, x cube, so on, are a basis of the vector space of polynomials. Yeah, and in fact, any I mean, this is over reals and complex. Any polynomial set of degree 0, 1, 2, I mean, I'm counting this constant as degree 0, is a basis. So what are we doing? So what we are doing is we are finding a transformation from one basis to another. So you can write this in matrix form, and we'll take advantage of this fact at some point. And it's a very common problem. I mean, this is a very common problem. This is a very deep thing that you have one polynomial set, you want to write it in terms of something else. I mean, it's the same thing as, say, Fourier analysis. You're writing something in terms of something else. So it's a very, very common theme in mathematics and shows up all the time. Maybe one side is better than the other side for some reason, right? So this is a polynomial in degree n in y with some q's in it, and this is also a polynomial. This is a polynomial expansion. That's all it is. And it you can have possibly a converse too. You can have y raised per n equal to something, and you get somewhere, and you will get to things like that. So those have direct application. They're called inverse relations. They have direct applications in mathematics. Okay, any queries so far? Any questions?
No, Professor. Could you give an example of how this new set of basis could be more useful?
Yeah, that's a tough question. It's a good
Oh,
question. I don't know the answer. Um, so, I mean, it looks nice. So it's useful to some people who appreciate nice things. Other than that, well, let's see. Maybe we'll see some examples. I don't know. Let's. I mean, these things are related to. These are combinatorial objects, so they are related to something or the other. So maybe we'll see something. But yeah, I don't know. I mean, I don't usually think in terms of usefulness and all. So it's hard for me to answer that. All I can say is that if Furstenberg found it and it was, useful somewhere in physics, then it must be useful. So this Q commutation business is somehow very central to things. And as far as we are concerned, this Q is sort of refining the other theorem. Uh, so the Q binomial theorem often comes up in that kind of context. But because it's a polynomial going into another polynomial, it takes another domain. I mean, so physicists will be interested and so on, because you're representing something in another way. But I don't know exactly where it's used or what. I don't really care also. Anyway, any other queries, comments? Okay. So I just want to mention that we also there are some. Let me just write it down. So we have sort of seen some binomial coefficient identities. So before leaving, I mean, I still have a lot to say on paths, probably next time. But before going to a more detailed look at paths, I want to um, just mention a little bit about binomial coefficient identities because these come up all the time in combinatorial. So let me say this, that there are about a million, I would say, also binomial coefficient identities. By the way, um, do you know who Moriarty is? Does anybody know who Moriarty is or was?
Professor, the Sherlock Holmes one.
Yeah. So if you look very carefully, Moriarty was a professor of mathematics. He was an evil genius, as many of your professors are, and uh, and he was an expert on binomial coefficient identities. Apparently, he wrote a thesis on binomial coefficient identities, as per Sherlock Holmes. And there are two, three identities which are known as Moriarty's identities in his honor. So there are literally millions of these. They come up in computer science all the time. And Knuth, you heard of Knuth? Von Knuth? So he wrote a book. He wrote a series, and he's still writing a series of books called um, "The Art of Computer Programming," and he spent many pages uh, discussing these identities. But all of them are pretty, they're pretty easy to do. Some of them are very complicated, but all can be proved. I mean, you have to be clever to do that, but essentially all can be proved using combinatorial means. It's not very interesting anymore to do that, or via generating functions. And by generating functions, I mean um, the binomial theorem or its extensions. So here I want to note a few. Which are very useful. So one is, just to remind you, 1 plus x raised per n is n choose k, x to the k going from 0 to n. So I've got rid of the y, and the first one is just put x equal to 1, and you get 2 raised per n, which is equal to k equal to 0 to n choose k. So this shows, for example, that the number of subsets of an n set is 2 raised per n, and vice versa. Um, it's kind of obvious from counting strings. So let me just give you a green proof here. This is number of strings of length k, length n with k ones. Yeah, and then here I'm add all of these up for all k. When you add up, you will get number of binary strings of length n. And how many of those are there? These are by multiplicative principle. Should just not write fast. I mean, each guy is either 0 or 1, so there are two possibilities. So they are 2 raised per n in number. So, I mean, this is the simplest of them all, and one can prove it this way. Uh, this is more fun to prove. Put x equal to -1, and you get summation n choose k, x to the k going from 0 to n is equal to 0 if n is bigger than 0, but when n is 0, then this is just 1. So it's a delta function, which is defined as this. So wait a second, what am I doing? I have to put a -1. So what this says, what does it say? It says that if you have a Pascal's triangle, then if you do, 1 minus this plus this minus this, then you should get 0. Minus plus, you should get 0. That's what it says. And for n equal to 0, you get 1. So these millions of binomial coefficient identities are essentially patterns in Pascal's triangle, and that's why Pascal's triangle is so useful. And since there is a link with binary strings, you can imagine that computer scientists would be extremely excited about it. So, I mean, binary string are useful in real life. Let me put it like this, at least for computer science. Anyway, one of the master identities which I want to show you, which more or less covers many of Knuth's identities, is called 2 van der Waals. And this shoe is uh, uh, this is 1303, and this guy is some 1700. I don't know what. So, I mean, he's a European mathematician, but it was known earlier, and it could possibly be known in India. But it's a very ancient identity, but it's extremely useful. And I'll just write it down first of all, then you do it. So L equal to 0 to A, and choose L, and choose K minus L. This is equal to N plus N. So how does one prove it? So proof one. Okay. So um, this is a L subset of IN, and this is a K minus L subset of IM, and this is a K subset of N plus M. So recall what is IM? It's 1, 2 up till N. So basically what you're saying is that you you make a K subset of IN plus 1, which is 1, 2 up till N, and then N plus 1 up till M. And these guys are M in number, these guys are N in number. So you pick L from here, and you pick the rest from here, and this can be done in so many ways, and then you sum over all L, and that gets you. Is that clear?
Yes, Professor.
So I mean, this is one of the obvious ones, but well, this is a proof which is special to me because it was shown to be my good friend in high school. So when I went to high school, which was much before you were born, probably, um, definitely before you were born, um, there used to be there used to be a chapter in our book, in our NCRT book, which was all about binomial coefficient identities. So this friend of mine, he was really smart. He showed me how to do all of them in one shot. So all of them were special cases of this, basically, where n was n, m was n, and whatever. So here's the proof. You take 1 plus x raised to the power n, multiply it by 1 plus x raised to power n. You have 1 plus x raised, right? And now this is L going from 0 to n, and choose k, uh, x raised to power, sorry, L. And this is I don't know, something else, m going from 0 to m, n, so this is capital N, choose m, x raised for m, and this is m plus n, choose k, x to the k. Okay, so all you do is compare coefficients of x to the k on both sides. And that is okay. Is that fine?
Yes, Professor.
Okay, and I'm at the end of my notes. So let me. Any questions, queries? I mean, I have something which I want to do, but that will take